plate fuel element. So my nuclear fuel is plate type, which means that it is a 3-dimension, looks like this. Again, I'm not going to draw anything in 3-dimension after that. I'm just showing you the original fuel plate for a purpose. Okay, that's my nuclear fuel. Okay. So far, if I leave it that way, that's not nuclear fuel. What make it nuclear fuel? That guy has a Q dot. I'm going to call the thickness of this guy, instead of used to call the L, in the case where no heat generation is involved, I'm going to call that TS. And that nuclear fuel is generating heat, right? And the heat is going from this face out, and the back face also out. And we usually ignore what is going out from the upper, the bottom, the front, and the back, because these are the most surface area that is going to actually dissipate energy out. So keep in mind, we always ignore that part, the bottom face, the front face, and the back face. Again, because we are dealing with 1-dimension problem. So heat is only picked to go in one direction. And this direction I picked up here is the one that has most of the heat dissipated out. So how we're going to simplify that? Again, we take a projection, and we will deal with the 2-dimension drawing all the time. So that's my plane wall, very similar to what we did before. Thickness here is 2s. And because of the nature of the symmetry of that problem, we're going to draw a center line here. Then we're going to assume the x coordinate starting from this line here, and that's the x direction, which is telling me that x is equal 0 where? At the center of the fuel. Remember, that's my fuel. For that front face here, the coordinate x is equal to s, right? Because the total thickness is 2s. Now this is half of the thickness. What about the other face? It's x equal to minus s. Remember, this is coordinate system. There is positive and negative, and the 0 starts from here. So anything measured in that direction is positive. Anything is measured in that direction is negative. Then I will add Q dot inside this guy. When I say there is Q dot, it doesn't mean that the source of heat generation is here. No, it's not a point source. That Q dot, it's everywhere. And we're going to learn about this later on when we talk about the transformation of neutron flux into heat. But Q dot just a symbol to tell you that, hey, pay attention, this body is generating heat. But where is it? We don't know. Okay? Just keep that in mind. Now, because of the symmetry situation, I can more simplify that by just drawing half of it. And whatever the calculation we are doing in the right side is going to equal to the calculation in the left side. And that's normally the case. We have symmetry. Remember, that fuel is supposed to be exposed to what? To coolant. Right? Or maybe there is a gas gap first. Maybe there is a cladding. Okay? But it depends on the situation. We're going to look into that. But what I'm saying here, there is energy going out in both directions. And we always try to keep everything symmetry. So if I have a gas gap, it's going to be on the right side like the left side. If I have a cladding, it's going to be on the right side like the left side. If I have a coolant, it will be very similar in the right side and the left side. So I can, in a simple presentation here, I can draw the center line and only half of the fuel plate. So the x coordinate system starts from here, x equal 0 here. This is now how much that thickness is. It's now only s. So this is x equal s. There is a heat generation in this body, right? Let's recall that surface here, temperature is Ts, surface temperature. Okay? Then, because there is internal heat generation, there is heat is going to that direction by conduction inside the fuel, right? Whatever that Q, I'm not interested on how much inside the fuel. What I'm interested in is how much of that energy will come out from that face, because this is what's going to my coolant, right? So this quantity of Q that's coming out from this face here, we call it actually Q from the surface. Like this is the temperature of the surface. This is the Q coming out of that surface. Okay? Okay. So now let's see how we do the analysis. Again, it's not required by you to memorize it or to, to follow it or to do it, but the final results can be used directly. And I'm showing this as a case study. Okay. What geometry is this? This is plate type. What is the governing equation? It's only one equation, but has different format based on the geometry. So the only equation that I know that can actually explain the conduction in nuclear fuel is partial 2T by partial x squared plus Q dot divided by K equals 0. And K here is referring to the K of that fuel, right? Okay. What do you want from this equation? What this equation can give you? Actually, this equation can be used to develop or to drive the temperature as a function of x, right? How? Very simple. I can take that term to the left side, so partial 2t by partial x squared should equal to minus q dot over k. What if I decided to integrate both sides? If you integrate the second derivative, it's going to give you the first derivative. If you integrate this, we know that q dot will be a constant value. K is going to be a constant value. So this is simply a constant value. So this will be minus q dot over k times x. And don't forget the constant of the integration. Let's actually integrate this equation one more time. So you integrate the first derivative. I'm going to get the temperature as a function of x. You integrate that, minus q dot over k is constant. X integration is going to be x squared over 2 plus c1x plus another constant for the integration. So the first lesson I have learned from this is the temperature distribution in this guy is not linear. It's parabolic. That's why the assumption that we did with a plane or flat surface that doesn't have a heat generation, and we said the assumption it's linear distribution, that was correct. Here, linear distribution does not apply, which means that I'm expecting, if I want to plot the temperature distribution, is going to be a second order. Remember, this equation showed the temperature distribution everywhere. So this equation will show that temperature distribution. So this is T as a function of X. I got it here. Remember, X is measured from here. X is equal 0 here. X is equal S in here, whereas S is the thickness, half thickness of the plate, that face. This is what we call it TS. And then I will have some energy coming out, which I'm interested, that's called QS. So that's number one that we learned from this equation. What if you want to get these coefficients C1 and C2? You have to use something called boundary conditions, right? What are these boundary conditions? What is the boundary of that geometry here? The boundary is, this is one boundary, and this is one boundary. And I need to find the relationship between X and T. So the first boundary condition is at X equal 0. At X equal 0, what's happening? Oh, it seems to be that my temperature is actually maximized. So I'm going to call that Tmax. What is the slope of a curve that's max? Slope is 0. What does that mean? I can say that partial t by partial x equals 0 at each value of x equals 0. That's one boundary condition. Let's apply this boundary condition. This is the relationship between x and partial t by partial x. This is not partial t by partial x. It's right here. I can put this guy 0. Partial t by partial x 0. If I put x equals 0. If this is 0, this is 0, I will get the first coefficient C1 equals 0. So this boundary condition will give me C1 equals 0. I'm just explaining the approach, the methodology. You are not required to do that. But I'm giving extra information for those interested to learn. Okay, what's the second boundary? Second boundary is here, which is at x equal s. what is the temperature? We call that temperature is actually Ts. So the temperature at X equal S is called Ts. So this is the relationship between X and T. So I can use this equation here. I can remove T of X, call it Ts. Under one condition, I take each X and give it S. So this will be S squared. C1 is already canceled out. It's actually 0, and that's plus C2. Now I can get C2 as a coefficient. That's Ts plus Q dot over 2K S squared. Then you can take C1 and C2, substitute into the equation, and when you do that, I will get you the final form. The final form, you will have T as a function of X. It's simply equal to minus Q dot over 2K X squared plus T max. So instead of actually getting T surface, I was able to get that as a function of T max. So this is the equation that you can use to calculate the temperature at any coordinate X. If you know what's your maximum temperature, say this is 1,000 degrees C. If you know the value of Q dot inside that fuel, if you know the thermal conductivity of that fuel, at each value of X, let's put X equals 0 in this equation. If you put X equals 0, what is the temperature at X equals 0? It's T max, which is true. Let's put the X equal S. If this is S squared, yes, that's S squared. So Q dot S squared over 2K plus T max, this is negative. Temperature will goes down. It will give you the temperature at the surface temperature. Okay? And what K is this? This is K of the fuel. So I'm going to call that K of subscript F, which stands for the fuel. Because if we have the gas gap, I'm going to call K gas. If I have cladding, I'm going to call that K cladding. So just to distinguish between fuel, gas, and cladding. Okay, so that's very important equation here. So the first use of this equation, you can use this equation, use the equation to calculate temperature within the fuel at any position X. Okay, so if I told you that thickness is 10 millimeter, what is the temperature 2 millimeter from the center line of the fuel? You're simply going to take X equal 2 millimeter, you convert that into meter, you calculate the temperature distribution. So you can actually construct that profile. You can easily construct that profile by just dividing the fuel into multiple locations, substitute for X with different values. You're going to make a table, you can actually plot that one. So that's the first use of this equation. So that's great. Now we can get the temperature. But the second important value I need to get is this. How much heat will be dissipated out of the fuel? So I need to calculate Q. Q is coming by conduction, right? It's moving inside the fuel. Heat is moving by conduction. But I need how much will leave that surface. So let's actually first calculate how to calculate Q conduction. Q conduction has only one equation, minus Ka partial T by partial X. That's Fourier's law. Now this equation is very useful because I can get partial T by partial X. Okay? If you go a few steps back, partial T by partial X was minus Q dot over Kx plus C1, and C1 was 0. So I can actually get partial T by partial X either by going back few steps and put C1 equals 0 based on that boundary condition, or you just make a derivation for this equation, right? So you're going to end up having Q equal to minus Ka, and partial T by partial X is going to be actually minus Q dot over K times X. So you'll find that Q is equal to, minus will cancel out, K will cancel out, so I will end up having Q dot times A times X. What? Q is no longer constant within the fuel. Now Q is also a function of X. And that's why the problem is complicated. I cannot have a thermal resistance to replace that nuclear fuel because in one single thermal resistance, that current should be constant. Now, Q is function of X. If X equals 0, Q is 0. If X equal 1 millimeter, I will get different value of Q. If it's different. Okay? That's why we couldn't use the thermal resistance technique that we covered so far to analyze the nuclear fuel. It's because Q is also a function of X. Which value of Q I'm interested in? I'm not interested in Q after a small distance here, or here, or here, or here. What I'm interested in is Q that's going to leave that face. What is the coordinate of that face? X equal S. So if I come into this equation and put X equal S, this will give me what we call it QS. So if you want to calculate QS, it's going to be simply Q dot times A times half of the thickness. Let me actually push that piece of paper up. Okay, so let me draw the fuel again. Half of the fuel. We concluded that temperature distribution is a parabola, starting with T max here, end with T surface here. That's my X coordinate. X equals 0 for that face. X equals S, whereas S is the thickness. We call that K of the fuel, and that guy has a Q dot. Then I'm interested on QS that's leaving that face. Either going to a gas gap or going to a cladding or going to a coolant. It doesn't matter. I need to know how much energy will leave that face. And this is the answer. Okay. Let's look to this equation here. If I multiply A times S, what is this? What is A first? A, again, is still the area that you don't see. A is this area here, the area perpendicular to the flow of the heat. So the area that's going inside the page times S, what is this? That's a volume. This is the volume of half fuel. You guys recall that energy generated is equal Q dot times the volume? This is exactly the same. So Q dot is uniform internal heat generation times the volume of that part will give me the quantity of heat going this way. But we know that the total fuel thickness actually has another S. So that should be A times 2S to get the total in the fuel. But we know because of the symmetry, half of it is going to go to the right side, half is going to go to the left side. So this equation is valid for that half here. But because of the symmetry, that QS will leave from the left face of the fuel as well. Okay? So that volume will change depending on the geometry. Okay? And that geometry we are dealing with is S, which is the half of the thickness of the total fuel thickness times the area that's going to the page. Then we can manipulate the equations a little bit. I'm going to end up having rearrange for the temperature. I can get this equation. T surface is equal to minus Q dot over 2 Kf S square plus T max. What I did actually, I went to this equation. I want to calculate the TS. So what is the coordinate of that TS? It's X equal S. So I put X equal S in this equation. So it becomes minus Q dot over 2K of the fuel S square, T max, and this should give me TS. Okay. So T max is the maximum temperature at the center line of the fuel. TS is the surface temperature of that fuel. Okay. We don't need that anymore. So can we rearrange this equation a little bit? Yes, I can bring that term to the right, to the left. So Q dot over 2 Kf equal to, S square is equal to Tm minus Ts. Can you isolate Q dot from this equation? Yes, Q dot can be written as 2 K of the F of the fuel divided by S square times T max minus Ts. I will take that Q dot into this equation. So I will have QS is equal to 2KF divided by S squared times TM minus TS multiplied by A times S. S go with the square. So I will end up having Q surface, or Q that leaving that surface, is equal to 2 thermal conductivity of the fuel divided by half of the thickness of the fuel, which is 1S here, times T max minus T surface. Does that remind you of something here? That's actually a delta T between these two faces. And that QS is leaving that face. Let's rearrange the equation. So I will have delta T, which is this term, divided by QS is equal to S over 2KF. What is delta T over Q? Go back a little bit backward. This is what? This is thermal resistance for conduction. Can be calculated from this equation here. It is the thickness of that half fuel divided by 2 times Kf. And this is a thermal resistance for plate surface or plane surface that contains Q dot. So let me put side by side the two different resistance that we have for plane surface here. So originally, we used to have that wall has a thickness L, thermal conductivity K, right? And there is area going inside this body here. And we have T1, T2, right? And there is conduction going through. In the second case, and that temperature is changing linearly, it's a line. The second case is the same wall, but that's a center line actually that we have, right? So the thickness here called S, thermal conductivity called K fuel, and this was T max, and this was T surface. And the temperature distribution is a second order equation. And this guy has a Q dot, and that Q is going out from this face, that's Q. In this case, we are getting QS. I can remove this guy and presenting a thermal resistance between T1 and T2. This is R thermal. What type? Conduction. How you calculate it? It's L over Ka. That's the R thermal conduction for this guy. As soon as I added that Q dot, things changed. Now I can add a thermal resistance between T max and T surface. Remember what was going here? That's Q. What's going in here? That's QS. This is the quantity that is going to leave that phase. This is thermal resistance. It's also conduction. And according to the equation that we drove a few minutes ago, it's R thermal is equal to S, L, it becomes S. But remember, this is the full thickness. This is half of the thickness, right? You can consider the full thickness of this divided by K, right? I think I missed A into this equation, right? We are missing A here. So this A has to go into here too. Okay. So this is S, which is the thickness, divided by K became K of the fuel. A remained the same, but there is 2 into this equation. So this is the thermal resistance of plate type, no heat generation inside. This is the thermal resistance for conduction in a plate type, but it contains heat generation. So now I can use thermal resistance for plate type nuclear fuel, and this is the new equation I'm going to use. Whereas S is the thickness or the half the thickness of the fuel. K is the thermal conductivity of the fuel. A is still the area going into the page, but there is extra 2 into this equation. And I show you how I drove that equation out. Again, that's the final result that we're going to use like this, and you don't have to drive any equation, but it's good to learn about the methodology, how we reach out to this. So that's how we can deal with that nuclear fuel plate type. We're still under the plate type. So now let's assume now I have a plate type fuel. So let's assume that I have a plate type fuel, and I attached a cladding, directly cladding to it. Then I expose the cladding to a coolant here. So that's a coolant, which means that I have T infinity and H. That's cladding. That's a solid material. I'm going to give it thermal conductivity K cladding. I'm going to give the thickness of that cladding C. That's my fuel. How I'm going to distinguish that? I will find there is Q dot here. Let's assume the thickness or half the thickness of that fuel is S, and the thermal conductivity K fuel. Okay? We know that, number one, maximum temperature will be here. That's default. I'm going to have a parabolic temperature distribution, and I'm going to call that TS. You can call it any other temperature. Then I will have temperature here. I'm going to call that T cladding. In the cladding, it's solid, but it doesn't have heat generation. I will go back to the original assumption that everything changed linearly here. So the temperature will change linearly. Okay? Then I know that there is certain quantity of heat will be dissipated from the nuclear fuel, and that quantity, it's called what? It's called QS. But this quantity QS used to be function of distance here, whereas X is here, right? But as long as it comes out from here, it's going to be constant. So that QS will continue in the cladding. Why? Because the cladding doesn't have heat generation. Everything is messed up because of the heat generation. So that's still going to be QS. That lift the nuclear fuel, it will continue through the cladding. It will go out from that cladding. Then it will jump to the coolant after that. All of these are constant here. So as soon as you leave the fuel, nuclear fuel, it's Q goes back to the constant situation. Nothing changed. So if I want to solve that problem, how I'm going to present that problem? Very easy here. Now, what is the absolute maximum temperature? It's going to be here. So I'm going to add a node here, call that T max. Then I'm going to have an interface temperature. We call that T surface. Now I'm going to call that surface temperature TC. Then I'm going to have the fluid temperature, which is T infinite. Now I'm going to do thermal resistance analysis. I know that there is weird conduction happening here. That's complicated function of X, but I can present that with a resistance. I'm going to call that resistance of the fuel. Then I'm going to have a resistance here called the resistance of the cladding. Then I'm going to have resistance here for resistance for the coolant. When we go back one slide here, what was the quantity of heat going here? At QS. Based on that assumption here, that derivation here, that's QS. So what's going in that fuel is QS. But QS is not going to change anywhere else, so which means that all of these resistance, we will have QS going through. Okay? Now, how we calculate RF? RF, that's a fuel with heat generation. So it's going to be the thickness S divided by 2 K of the fuel times A. What about the cladding resistance? R cladding. Now, there is no heat generation here. I go back to the thermal resistance where no heat generation is included. So this will be L over Ka. L here is called C. K is going to be K of the cladding times A. What about R out? That's a convection, right? That's a convection happening here. So it's 1 over H times A. Now, I can calculate 3 different resistances. Then I go back. Oh, how you want to calculate QS? QS is equal to, again, assume this is the only 2 temperature that you have, T max minus T infinity. You have to divide by the equivalent resistance. They are all in series, so it's going to be R fuel plus R cladding plus R coolant. Then I can use this same quantity of Q. If I want to calculate the interface's temperature here, I would say this is T max minus T surface. I will divide by R fuel. This equation will give me the T surface. I take the same Q and say this is equal T cladding minus T infinity divided by R of the convection. From this, I can get T cladding and so on. So all what we did now, we were able to use the general energy equation in one dimension, considering heat generation, steady state condition, to drive equation for the temperature distribution, equation for Q. And we were surprised that Q is also function of X. So we were only interested in the quantity of Q that leave the nuclear fuel. Then we were able to put the equation together to drive a formula for the thermal resistance for an equivalent nuclear fuel, whereas heat generation is included. Then now I'm showing you the application if you are combining nuclear fuel with heat generation to any other plane wall or plate type, how to use the resistance that we learned before the heat generation and integrate the resistance for heat generation into the problem. I think that's make things much easy now when we analyze a full nuclear fuel, maybe followed by a gas gap. Let's assume that we have a gas gap. You're going to add another resistance, and there's going to be conduction in a gas gap. It's going to be L over Ka, very similar to the solid, because in the gas, we assume it's conduction. So we are treating it as a solid, and just one additional resistance. That's simple. So I hope that give you the idea on how we analyze plate type nuclear fuel with other gas gap or cladding or coolant that's included in the problem.